Hello. I thought in addition to the live streams that I've been doing, you might want to see me go through a past chemistry paper. So I thought no better place to start than last year's foundation paper. Now, the new 9 to 1 GCSEs actually have some overlap. So you'll actually notice that the last two questions of the foundation paper are exactly the same as the first two questions of the higher paper. I will make sure I get to those higher questions tomorrow, as well as a planned live stream before the exam. First of all, let's get into it. Question 1. Okay, figure 1 represents an atom of sulfur, and you can see here it's picked it out. It's exactly the same as it is on the periodic table up here. First of all, it then asks you to look at the table and complete the number of particles in a sulfur atom. So that first of all relies on you knowing what those first two numbers mean. And actually, if you're ever stuck, it's given to you in the exam. You'll notice here that it says that the top number is the relative atomic mass and the bottom number is the proton number. So you don't even actually need to remember that. So when we're having a look here, we know that that top number 32 is what we refer to as the mass number. That is the number of protons and neutrons in the nucleus. This bottom number here is the proton number, or we more correctly call it the atomic number. And as the name suggests, that is the number of protons in the nucleus. So, if I've got 16, atomic number of 16, that means that I have 16 protons, and indeed that's already filled in for me in the table. Now the only particle not mentioned here is the electrons, and the electrons must equal the protons. That's because in an atom, it is neutral. If you remember, a proton has positive charge and an electron has negative charge. So if I have uneven amounts of electrons and protons, I suddenly have a problem. Okay, and that atom is no longer neutral, it's actually charged in what we call an ion. So neutrons, well, if I've got 32 protons and neutrons, 16 protons, the key here is I'm going to take one from the other. Okay, so that'll be 32 minus 16, which gives me 16 neutrons, sorry. Okay, sulfur is in group 6 of the periodic table. Complete the electronic structure of the sulfur atom. Well, first thing to remember here is it's in group 6. So whatever happens, I must have 6 electrons in the outer shell. If I have a look, okay, here it's 16. Well, we've already been given that. There's 16 of them there. Now, if you even if you didn't remember that it's 2, 8, and 6, 2, 8, 8, and so on with the electron shells, if you notice that it's in group 6, I could put 6 in the outer shell already, and by process of elimination, given the fact I've got 16 and I've got 6 in the outside, 2 in the middle, that means that I've used 8, and that means I've got 8 left. So notice how I'm using the information that I've been given and I'm working through it. Okay, 1.3. Sulfur reacts with oxygen to produce sulfur dioxide. Complete the word equation for this reaction. Right, so first of all, because it reacts with, I know that I can substitute that for a plus. So when it says sulfur reacts with oxygen, it's going to be sulfur plus oxygen to produce. Now that is our kind of word signal for an arrow. Okay, so that means that there's been a change, and I get told that it produces sulfur dioxide. Okay, there we are, we're using the question against itself. What effect is caused by sulfur dioxide? So as soon as I see sulfur dioxide, my alarm bells go, okay, and I start to think that is the acid rain chemical. If you're not sure about that, let's have a little think. Okay, sea levels rising is kind of like a secondary effect that's caused by something like global warming. Now, we haven't really mentioned sulfur dioxide with global warming, that's carbon dioxide, and that's where that one's trying to trick you out. Global dimming, okay, global dimming is all to do with particulates from incomplete combustion. Okay, acid rain is our sulfur dioxide. and also nitrogen oxides. Okay. Figure 3 shows the mass of sulfur dioxide in the Earth's atmosphere between 1984 and 2014. The student said the mass of sulfur dioxide in the atmosphere decreased every year between 1984 and 2014. Is the student correct? Use data from figure 3 to justify your answer. So first of all, we need to give some form of judgment about whether the student is correct, and then crucially we must use data. We must read off the graph at some point. Well, let's have a look. 1984, we start here at 3,500. Okay, I can read that off the scale. It goes up to 3,900, where it remains constant for 3 years, and then it decreases initially quite rapidly and then has slowed. But the key thing here is we've gone up between 1984 and 1987, so it has not decreased every year. Okay, so the first point I'm going to say is between 1984 and 1987, the levels of sulfur dioxide increased. Okay. Now's a really good time to use those numbers. So it increased from 3,500 kilotons. Okay, that's the units. It says mass of sulfur dioxide in kilotons, to 3,900 kilotons. This means the student is incorrect. Notice how I'm linking back to the question there. It's very easy to get caught up in some really frilly language in science. Okay, all you really need to do is say this happens, therefore this happens, bosh. Okay, don't need to mess about, don't need to keep it interesting with any fancy language. The one exception to that is to make sure you're using technical terms. That's not really using fancy language to like keep the reader interested. That's more just using the correct scientific terminology. If I have a look then here, okay, it says figure 4 shows the percentage of sulfur dioxide released by human activities. Calculate the percentage of sulfur dioxide released by industry. Well, the first thing to remember is that added up together, that will be 100%. Okay, now industry is the only one not given a number. We've got 6% for transport and 69% for electricity generation. So 69 plus 6, which is 75%, is already accounted for. Okay, now this kind of makes sense because this looks like a quarter, and if you remember, a quarter of 100% would be 25%, but we want to make mathematically sure. So that's 75%, so 100 minus 75 equals 25%. So therefore 25% was by industry. Okay, that is question 1. Question 2, so we're now on chromatography, which is part of the chemical analysis unit. Okay, a student used paper chromatography to identify the colours in black ink. Figure 5 shows the student's results. Okay, what colours are in black ink? So the first thing to remember in chromatography is that dots which get to the same height and the same solvent we decide are the same substance. So if we have a look here, this red colour and this dot here, we can see they're at the same height, so that means that red must be in the black ink. If we have a look here, green, that does not match up to anything, so therefore green is not in it. And blue, okay, clearly matches up there, so it is red and blue. Suggest which colour is least soluble in the solvent. So the key thing here is to remember that in chromatography, the more soluble we are, the more you move up the paper. Okay, I like to think about it as I've come home, okay, and I've brought my shopping. Okay, I've got one bag here which is really heavy and it's boring, I don't care about it. Okay, so that's my food or whatever. Okay, here, okay, I've got like sweets. Okay, and here I've got the latest game. Okay, now the one that I'm more interested in is the game. So when I climb up my block of flats and the stairs, okay, and I get tired, the first thing I'm going to do is get rid of that because I don't care about it as much. Okay, the next thing I'm going to get rid of as I get more and more tired is the sweets, and finally it's the PlayStation games because I actually want them. Okay, so the colours which are dumped off first are the ones which the solvent likes the least. Now I know we don't want to think about the chemicals as actually having a personality, but that's a good way to think about it. So the colour least soluble in the solvent will be the one which has travelled least distance up the paper. In this case it will be red. Okay, and the reason is because it has travelled the smallest distance up the chromatography paper. Okay, you question 2.3, use figure 5 to complete table 2. So this is where you get your ruler out. Okay, obviously I'm so prepared I didn't actually bring one. Okay, so the green colour here I'm going to say is about a centimetre. Okay, will be 10. Of course you need to measure this with a ruler. Now it doesn't really matter actually where you measure it from. I would say the base of the dot or the top of the dot. I know that's not particularly helpful, but in reality you just need to be consistent. You'll also make sure that you'll get a range of possible values in here, and the dot kind of size will be taken into account here. Then we need to measure the solvent front. Okay, I'm going to say that that's about 3 times 32. Now I've just plucked those numbers out of the air. Key thing here is that you measure them with a ruler. Okay, now we put it into the equation. Okay, we get given the equation. So RF is 10 divided by 32. Okay, which is a number. Okay, you get that on a calculator. That'll actually be 5/16. Okay, which is roughly a third. Okay, I know I've done some weird fractional simplification here. All you need to do is stick that into a calculator, and that will be about 0.3. So I can put that in there. Okay, now I would actually do this to 2 significant figures. Why is that? Because I've measured these to 2 significant figures. Now I know that's probably one of the worst kind of YouTube going through a question in the world. That's because A, I didn't use a ruler, sloppy, okay, and B, I didn't use a calculator, right? Those 2 things, very crucial, but the method is the same. Okay, all I've done is I've taken the numbers from the paper and I've plugged them into the result, into the equation I've been given. Okay, question 3. Student tested a seawater sample for dissolved solids. Figure 6 shows the apparatus. Okay, what is apparatus X on figure 6? Okay, well, first of all, let's look at here. We need to use a process of elimination. Is it a tube? No, it clearly can't be a tube, so therefore it's definitely not a boiling tube. Is it condenser? Well, there's nothing kind of cold there. Okay, if you remember, a condenser is what we attach to cool things down. A condenser is the piece of apparatus which kind of looks like that. Okay, and we can fill this with water, and that gets the kind of tube through the middle nice and cold, and that condenses the liquid. So it's not a condenser. Hopefully we all know what a funnel looks like. It's clearly not a funnel, and that only leaves a watch glass. Question 3.2, the student did the test 4 times. Now this is classic annoying, okay, and actually they've even given you the hint in the question. Whenever you do a mean, okay, whenever you get asked to do an average, do not include the anomalies. Okay, always look for an anomaly. If I have a look, they will also always make it really obvious. So if I see here, I've got 0.12, 0.29, 0.14, 0.15. This 0.29 here is clearly way out. Okay. Next thing to notice is when you've taken out the anomaly, you don't still divide by 4 in this case. You're now using 3 numbers, so you can divide by 3. So I'm going to do 0.12 plus 0.14 plus 0.15 divided by 3. Okay, and if I stick that into a calculator, okay, it will be 0.13 kind of like 6, like that. Okay, now here's where it says give your answer to 2 significant figures. I need to therefore round this, and it will be 0.14 to 2 significant figures. Make sure I actually write the right answer, that'd be good. Okay, remember, significant figures are the numbers after the 0. Okay, so we don't have to worry about the 0. We've got a 1 and we've got a 4. Okay, we've got a 1 and a 3, and then we'll round this 6 to make it 0.14. Okay, the student distilled a sample of seawater in the apparatus shown in figure 7. Here we've got it. Okay, you can see here we've got a kind of conical flask. We can evaporate the water here. The steam is therefore going to go over through the delivery tube and drip into the test tube. What change of state is happening at the surface of the seawater here? Well, seawater is a liquid. When I heat it, it's going to turn into a gas. So we're looking for the liquid to gas transition. What we say, okay, is boiling. Okay, it's boiling because you're really giving it some beans with a Bunsen burner. You could also potentially say evaporating, okay, but you wouldn't really say that you evaporate water in the kettle, okay, because it's a little bit more vigorous. Describe how the water in test tube, how the water in the test tube in figure 7 is different from seawater. Well, if we think about what's in seawater, it's mainly water and salt. Now, when I heat it up, the salt is going to stay behind. It's going to stay in the conical flask. The water is the only thing which is going to boil. You don't really have boiling salt in normal conditions. Okay, so the water is going to turn to steam, go over here and condense, whereas the salt is going to be left back here. So describe how it's different. Okay, the water in the test tube will not contain dissolved salts. Okay. Why does producing drinking water from seawater using distillation cost a lot of money? So this is the classic bringing it back to economic reasons. This is a lot of faff, right? If you're trying to make this to drink, you're having to boil water using a Bunsen burner, turn it into steam and condense it over here and capture it. And bear in mind that this apparatus is quite crude, and some of the steam is going to go psh and go out here anyway. So that's wasted energy. Boiling water takes a lot of energy. If you look at your electricity bills, or if you have a smart meter at home, the thing which overwhelmingly uses the most electricity is when you're heating stuff up. Okay, the kettle uses a hell of a lot of energy. So when I'm producing drinking water from seawater using distillation, I am using a lot of energy, okay, as heat is used to boil the water, and that is expensive. Okay, you probably don't have to pay your electricity bill yet, but when you do, it is not fun, I promise you that. Okay, river water is filtered then sterilised to make drinking water. Why are these two processes done? Okay, let's think about if I had the opposite, right? If I didn't filter it and I didn't sterilise it, okay, and I rocked up with a bottle full of river water. Well, if I got the bottle out of the river, okay, I'd have gunk floating about in it, and also because it's been from a river, okay, let's get classy. If I zoom in, okay, I'll have microscopic bacteria, okay, some of which can make you quite ill. So that's what river water would be like. So these two processes are going to counter it. So filtering removes kind of any insoluble solids. that are in the water. Things like sand, right? You don't really want to have a sandy bottle of water. If I filter it, I get rid of it. Sterilizing, okay? This is going to kill the microbes. Now we can think about what the sterilizing can be done with. It's either usually done by ozone or UV light, okay? And that's enough to kill the bacteria or any harmful microbes and prevent you getting ill. Next question, let's mix it up, let's go for green. Actually, I start off with green, let's go blue. No, I'll start off with blue, let's go green. What percentage of the Earth's atmosphere is nitrogen? Okay, just a fact you need to know, it's 80%. Okay, so if I think about what the atmosphere is made of, 80% is nitrogen roughly, oxygen is roughly the other 20%, and then kind of everything else is kind of roughly 1%. So that includes 0.04% of carbon dioxide. You don't need to remember that percentage. The idea is that you just need to remember that it's actually a very small amount. And then other noble gases. Water vapour is a bit more variable because obviously if you are taking a sample of air just above the ocean, it's going to have a lot of water vapour in it. During the first billion years of the Earth's existence, the amount of nitrogen in the atmosphere increased. Give one source of this nitrogen. Okay, if in doubt, volcanoes. Okay, if in doubt, volcanoes. They pump out the gases and change the Earth's atmosphere. Nitrogen is used to make ammonia. The word equation for this reaction is nitrogen plus hydrogen, ammonia. Now, this is hinting at something what we call the Haber process. Now, you don't need to go into too much detail, especially at foundation level, about what the Haber process is. But the Haber process is really important because, as it says here, is a reversible reaction. So what this is testing you on is if you remember the reversible reaction symbol. Now, hopefully you do, because I think it's the funkiest symbol in the whole of science. Okay, it's where you have a kind of an arrow where the top half is going that way, okay, and the bottom half is going back that way. And this is to show that the reaction can go from the reactants to the product, but also from the product back to the reactants. A reversible reaction can reach equilibrium. Complete the sentence. Okay, equilibrium is reached when the full reaction and the reverse reaction happen at the same what? Okay, now I always like to think about equilibrium as running up a down escalator. Okay, if you've ever had a rebellious moment, okay, and you're in a shopping centre, okay, or whatever, and you decide that you want to run up a down escalator. So the escalator is moving down, okay, and if you run up, now first of all you run up quite fast and you start getting up, but then you get a little bit tired because the chances are if you're being a rebel and running up a down escalator, you probably haven't done much exercise. So what happens is you eventually reach a point where you look like from the outside you aren't going anywhere. Okay, this is what we call equilibrium, because you are running up the escalator as fast as the escalator is running down towards you. Okay, well, not that the escalator is running, but you get what I mean. This point where you're running up at the same pace of the escalator going down is equilibrium, and the key word here is rate. Okay, because we don't obviously have a miniature escalator in our reaction. What we have is a rate of forward reaction, i.e. how fast that reaction is going that way, and a rate of backwards or reverse reaction. And as soon as they match, it's like running up a down escalator. Okay, fertilizers are formulations containing nitrogen. What is a formulation? Okay, formulation. I always like to think of kind of a baby formula, right? And that's the word. Whenever I think of formulation, I always like to think of formula. Okay, when I think of the word formula, I think about something like Formula 1, I think about maths and all of the stuff to do with that, and I also think of baby formula, and that's the one we're going to focus on today. So what is baby formula? It's a man-made equivalent of breast milk. Okay, so humans have decided that these are the components, looking at breast milk, these are the components that we need to raise a healthy baby, and we're going to put them all together in one container. So a formulation is a man-made mixture. Okay, man-made, designed mixture. And why do we design this mixture? Okay, it's to have specific properties. So for baby formula, the property is the ability to grow a healthy human. For fuel, because like you go to the petrol station, you have additives in the fuel. That's to get the most miles out of your car and also maintain a working engine. Okay, and here the fertilizer's job. Okay, it's a man-made mixture designed to give everything that a plant needs to grow. Okay, question 4.6, table 4 shows percentages of chemical elements in a fertilizer. So we've got 7% nitrogen, 3.1% phosphorus, and 5.8% potassium. Now this thing here, the NPK thing, is actually in the triple science, so we don't need to worry about that. Draw the bar for potassium in figure 8. So first of all, I need to make sure I know my scale. Okay, and you can see here that it's 5 little squares to 1. I want to get 5.8, so I'm going to start at the 5, okay, which would be here. Now 5.8 would be, if I was 5 little squares is 1, that means each little square is 0.2, so 0.8 is going to be 4 little squares. Again, I'd use a ruler but I'm a bit of a rebel, so there you go. And there we have drawn a bar. Hopefully that's not too bad. I quite like it. I think you should learn to love graph questions, because if you can do a bar chart, you can do a line graph, they are really nice bonus banker marks. A fertilizer contains 0.225 grams of iron per 3 grams of fertilizer. What calculation can give the percentage of iron in the fertilizer? Okay, hopefully we know, this just relies on us kind of knowing how to work out a percentage. If I've got 0.225 in 3 grams, that means that I've got 0.225 divided by 3 as a proportion. And the only thing which makes it a percentage is if I then times by 100. Okay, the only version of that which exists is this one down here. Okay, it's a bit confusing because they've decided to integrate the 100 into the fraction. Okay, and the easiest way, if you're not sure about this, is remember that 100 is the same as 100 divided by 1. So if that was a fraction, it'd be 100 over 1. And hopefully you know that if you multiply fractions, you do the top numbers together and the bottom numbers together. Okay, so for the sake of completeness, okay, and hopefully you recognise that 3.0 times 1 is just going to be the same as 3.0. which is this one down here. Okay, 4.8, figure 9 shows the use of fertilizer in 4 different countries, A, B, C, D. Very interesting names for countries. In 2003 and 2015. Okay, now much more fertilizer was used in 2015 than 2003. Is the student correct? Use data from figure 9 to justify your answer. So first of all, we're going to need to know how much was used in 2015 and how much was used in 2003. So, first of all, you know that he's going to be right, okay, and that's because 2003 is the pale grey and the darker grey is 2015, and all the bars are higher. The actual hinging word here, the weird word, is the much. Okay, so that implies it's got to be considerably more, not just a little bit more, but considerably more. So let's have a look about how much. So here, okay, I can see my scale. Each little square here is going to be 10. So in 2003, A is going to use 20. B goes up 7 squares, that's going to use 70. Only 1 square, so that's going to be 10. And 3 squares here, which is 30. So if I add those all up, that would be 20 plus 70 plus 10 plus 30 is 130. Okay, if I have a look at the 2015, well, I've got 20 squares there, so that's going to be 200. So straight away, that's actually more than all of 2003 combined. And that's actually a fact which we could use, actually. B is 120, C is 100, and D actually hasn't gone up that much, that's only 40. So that is 320, 420, 460. That is considerably more. It's over 3 times more. Okay, so is the student correct? Yes. Much more fertilizer was used in 2015 compared to 2003. Now is the time to use our data. In 2015, 460 kilograms per hectare was used compared to 130 in 2003. Okay, which is over 3 times more. And then, just because, you know, I like to throw in the cheeky fact, in fact A used more in 2015 than A, B, C and D combined in 2003. Okay. Question 5. Okay, 3 more questions left. Okay, a student investigated the effect of the size of marble chips on the rate of reaction between marble chips and hydrochloric acid. This is the method used. Add 10 grams of marble chips into the flask. Add 50 centimeters cubed of hydrochloric acid and start a timer. Record the mass lost from the flask every 10 seconds. Repeat steps 1 to 3 with different sizes of marble chips. Draw one line from each variable as the correct example of the variable. Okay, so hopefully we remember there are 3 types of variable. There's the independent, the dependent, and the control. Okay, now I always like to think about Beyonce, just because Beyonce. Okay, Beyonce is an independent woman. Okay, she chooses what she wants. Okay, she is the independent variable. The independent variable is the thing which you choose to change. Okay, so it's the thing which you go into the experiment and that you change every time. And if I have a look at this experiment, I did this thing here and then I repeated steps 1 to 3 with different sizes of marble chips. So the thing which I decided to change was the size of the marble chips. Therefore, that is my independent variable. The dependent variable is the thing which depends on the independent variable. Okay, it's the opposite of independent. It's the thing which is being changed, but we're not in control of it. Okay, so that is actually the thing which we measure. Okay, that's the thing which we measure. Now in this case, what are we measuring? Okay, we are measuring the mass lost. Okay, so the dependent variable in this would be mass lost. The key thing, if you're wanting to look at these from an exam point of view, is the dependent, you'll see the word measure or you'll see the word record next to it. Okay, the control variable is the things which you keep the same. Okay, because if you changed everything at once, your experiment would be unfair. Okay, so we only change some things at a time, and the things which we are keeping the same here, okay, well, we kept everything the same. The only thing we changed was the different size of marble chips. So anything up here which is not to do with the size of the marble chips is something which we kept the same. So we kept the volume of acid the same. Okay, I suppose we kept the size of flask the same, but it's not really as important. Okay, 5.2. The equation for the reaction is this: name 3 products. Okay, products. Okay. The key thing here is whenever you have a chemical reaction, you have reactants, and they are turned into products. Okay, and this is actually quite mean because they're giving you the symbols and they're expecting you to turn them into words. But that's not too bad. Let's have a look. These are clearly our 3 products because they are the things to the right of the arrow. Now, H2O. Hopefully we know that H2O is water. Okay. CO2. We see that quite a bit. That is carbon dioxide. These are just chemical symbols which we need to know. This one here is the tricky one. So I've got Ca, and if I look on the periodic table, okay, Ca is calcium. So I know it's going to be calcium something. I've got Cl2. So if I go here, Cl is chlorine. Now, hopefully you're aware that when chlorine reacts with something to form an ionic bond, it's not calcium going to be calcium chlorine, it's calcium chloride. Okay, so all we've done is we've taken what we know, which is the water and the CO2, and we've even used the periodic table to help us with CaCl2. Don't be afraid to reach for the periodic table, it is quite useful. Question 5.3. Another student suggests putting some cotton wool in the top of the flask. Suggest why this would improve the investigation. Okay, this is a required practical, so you should have done this. Hopefully you remember that when you add the marble chips, you see bubbling and fizzing. Okay, that's what you're actually recording the mass lost. Now, whenever you have a glass of Coke, okay, and you put it down on a table, you'll probably notice something weird, if it's especially very full and you can see the bubbles streaming up like this. Okay, if you put your hand on the top of the, look at this, I should have been an art teacher. Right, if you put your hand over the top, you'll actually feel it get a little bit wet, and that's because as the bubbles come up, they'll flick up bits of the liquid with it. Okay, you'll feel like it's almost like a sleety rain coming against it. So if I put cotton wool in the top, it's going to stop. So the cotton wool will prevent loss of liquid. So that means that the only mass lost will be from the gas. Because cotton wool is not going to stop a gas. Okay, gas can flow through it. Question 5.4. The reaction produces 1.6 grams of gas in 30 seconds. Calculate the mean rate of reaction for the first 30 seconds. Nice and simple. They've actually given you the numbers, they've given you the equation, it's just a case of plugging them in. So remember, I always like to use the acronym FUNKY. First of all, we make sure we've got the right formula, what's been given to us. Second thing is that we've got the right units. Well, grams, that's fine. Seconds, that's fine, so that's done. N is that we put our numbers in. Okay, so here we've got, so the rate is going to equal 1.6 divided by 30. C is calculate, so that's where you actually put the numbers into a calculator and work it out. That's going to be 0.053333, whatever. Okay, we don't want to never ever have recurring, okay, in science. Okay, we don't like to do it because that's a maths thing. Recurring implies that you know it precisely. We never know anything precisely. So we're going to round that to 0.05 will do, or you can have 0.053. Actually 0.053 would be more correct because that is to two significant figures, and we have been given our data to two significant figures. That being said, that could be one significant figure, so therefore 0.05 would be alright. Y is, you don't forget the units, okay? That's because originally I was going to use func-u, but that has the problem of sounding a bit rude. So you don't forget the units. So in this case, it's going to be grams. So grams divided by seconds. So the units, okay, going to be grams / seconds. All you've got to do is take whatever in the equations on the top divided by the bottom. Lovely job. What was the unit for mean rate of reaction calculated in there? Well, look, I'm already jumped the gun. That one. Okay. The key thing here is whenever you're looking at rate, you know that a rate has got to be divided by time or per time. Otherwise it's not a rate. Every kind of example of rate that you have is pretty much per time, right? It's how often you're doing something. And the only one here which has got something divided by s is this one. So we can use a process of elimination there if we're not sure. Okay, 5.6. Table 5 shows student results. Plot the data from table 5 on figure 11. Again, wonderful. We see a graph, we've got to love it. Okay, so 0 and 0. So remember, along the corridor and up the stairs, at time 0, the mass produced is 0. At time 10, it's 0.8. So if I have a look here, okay, 10 squares is 0.5. So that means that here is going to be 0.8 because This kind of thicker line in the middle is going to be 0.75 because that's halfway between 0.5 and 1, and then 1 extra square up. Okay. 20, okay, is 0.6, and that's a bit bizarre. It's actually gone down. Don't like that. 30 is 1.6. 40 is 1.8. Okay, notice that all I'm doing is kind of following my my scale. 50 and 60 are the same, and that's onto along like this. Okay, draw a line of best fit. Now the key thing, and that's why I've put that weird point in there, is they do not, I repeat, do not want to see this. That is not a line of best fit. That is playing connect the dots. You are not for. Okay. What line of best fit is exactly what it says. It's a line of best fit. Now, that can be straight, or it can be curved. They're all lines. Okay. Now, if I have a look here, if I ignore that point there and say it's an anomaly, I actually have a nice curve upwards here. So it starts off and it increases quite a lot, and then it slows down and actually comes to kind of a constant value here. Okay, be confident, draw one line and don't deviate. Don't start wiggling about and deviating for the points. Just do one line, use your arm and use your elbow and the fact that you can draw a smooth curve. Okay, question 5.7. The large marble chip has the same total volume as the 8 small marble chips, but a different surface area. Why do the small 8 marble chips react faster? Okay, this is where we first come to collision theory. Now, what collision theory does, okay, what it says is that to react, particles must collide, it's in the name, and they must collide with sufficient energy. So anything which alters one of those two properties is going to make the reaction faster. There are 4 things, well there's 5 things, but 2 of them are basically the same. Okay, there is temperature, or the Sean-Paul factor. Okay, there is surface area. There is concentration / pressure. They're the same. Concentrations in a liquid and pressures in a gas. And there is if there is a catalyst or not. Alright, so let's think about how these are going to affect them. If I have a faster temperature, the particles are going to move around faster. This means that they have more energy, so that means that this one is being boosted. Okay, so that's an increase in sufficient energy. And also because they're moving around faster, there's going to be more collisions. So temperature works on both of these. This makes sense, okay, if you're running around somewhere, you're more likely to bump into people than if you are walking. Surface area. Okay, this is how, we'll come back to that one because this is what this one is. Concentration / pressure. If I've got more particles in the same space, this means they're more likely to collide. Right? Again, think about this. If I had a room full of people and I put 10 extra people in there, there are going to be more collisions. A catalyst. Now what a catalyst does is this lowers it lowers the activation energy for the reaction, i.e. the amount of energy it needs, i.e. the energy which is we call sufficient, is less. I like to think about this as a theme park ride. Okay, imagine you have a sign which says you must be 1.6 meters to enter and ride the ride. Not everyone's going to be able to go on that because some people are short, right? But imagine you go back the next day and they've lowered that height of entry to 1.2 meters. Suddenly more people can go in on past the height restriction, and therefore there's going to be more people on the ride. It's the same thing with a catalyst. It lowers the activation energy, and therefore more collisions are going to be successful, and therefore there's going to be a faster reaction. So what that does is it kind of increases the amount of collisions with sufficient energy. Let's go back to the surface area. Now in a solid, the only place where I can react is on the surface, right? I can't magically get some chemicals to burrow in and react with the inside. So the only way it can react is if it collides with the outside. If I have more surface area, right, because these do have more surface area, because if I put some numbers to it, okay, if I make this 2, right, if I halve every side, you'll see that it makes 8 squares, the same as here. So that means each one of these has 1, sides of 1 like this. Yeah? If I take the surface area, that's 2 by 2, which is 4, so the front is 4. That means that that side is 4, that side is 4. So I've got 6 sides of 4, which is 24. Here, well, I can come here, I can come here, I can come here, right? That's one side of 1, 1, 1, and the other 3. So that means each cube is 6. So 6, 6, 6, 6, 6, 6. I'll number the devil. Okay. Overall, that means it's going to be 36, 42, 48. I've doubled the surface area. Right? That's a lot. But you know this in normal terms. If I had a collider of these, I'm coming at it from all angles like this. Right, I can bounce into this, bounce into that, all sorts. I'm exposing more of the solid to the solution. So that means that I'm going to have more collisions, and therefore the rate of reaction is going to get faster. So if I have a look here, the 8 small marble chips have a larger surface area, so less frequent collisions. Well, that's bit right, that bit's wrong. The 8 small marble chips have a larger surface area, well, we know that. So more frequent collisions. That's the answer. Okay, 2 more questions. Question 6. Crude oil is a mixture of hydrocarbons. A hydrocarbon in crude oil are separated into fractions by fractional distillation. Okay, it shows a fractional distillation column. Crude oil vapour passes up the column. Complete the sentence. Okay, so first of all, what happens in a fractional distillation column? You take the crude oil and you turn it into a vapour. Okay, and what happens is that vapour goes up here, and when it reaches the temperature at which it's comfortable, it gets out. Okay, it condenses and is piped off. Right? I like to think about this as kind of like a reverse sauna. Now I know that sounds a bit bizarre, but hear me out. Okay, if I imagine I get into a sauna and the temperature is slowly going down. Right? Now those kind of hardcore kind of sauna people will they'll it's a rubbish analogy. Just ignore that. Okay. Basically, what happens is they rise through and they condense at their boiling point. So up here it's colder than down here. Down here it is hotter. So when it reaches the temperature of its boiling point, it will condense and be taken out. Okay. So each fraction, and the key thing here is it condenses because it is added in as a vapour. Why do the fractions separate? And this is the key thing, is they have different boiling points. Okay. Yes, they do have different flammabilities, but that's not important for the fractionating column. Yes, they do have different melting points, but they're not going from solid to liquid, or liquid to solid, sorry. They have different viscosity. Yes, they do, but again, that's not how this works. It works because the gases are condensing, and that is all to do with boiling points. Most of the hydrocarbons in crude oil are alkanes. Okay, so figure 14 represents an alkane molecule. Name the alkane. Well, first of all, I need to have a look. I've got 1, 2, 3 carbons. Okay, those black circles are carbons. Okay, again, the key thing to think about here is if I think of coal. Oh no, what's going on there? Ah, you've been sacked. Coal is black, right, and it's made of carbon. Or graphite is black and made of carbon. So I've got 3 of them. Now, the 4 ones that you need to know are methane, so meth, ethane, F, prop, and bute. Now these, and after that it's the same as the shape, so like pentane, hexane, you know, like pentagon has 5, hexagon has 6, pentane has 5 carbons, hexane has 6 carbons. You might be thinking about where these come from. it's just weird. Don't worry about it. The key thing to remember, the way I always remember this is monkeys eat purple bananas, and that gives you the first letter, and then hopefully you can remember meth, eth, but, or methane, ethane, propane, butane. Now, because I've got 3 carbons, 1, 2, 3, this means that this is propane. Okay, CH4 methane is an alkane. What is the general formula for alkanes? It's quite complicated sometimes to think about this, but when I draw an alkane, what am I doing? Okay, if I draw butane, okay, now I haven't quite finished it yet, but you'll see why. All carbons must have 4 bonds. If they're not happy. So this one here, this carbon's happy, this carbon's happy. So when I'm drawing this chain, each carbon has got 2 hydrogens attached to it, right? So that means that for every carbon, so Cn, I'm going to have H2n, i.e. every carbon is going to have 2 hydrogens with it. So that's why we have Cn, H2n. If I have C3, that means I'm going to have H6. In this case, I've got C4, so I've got 8 hydrogens at the moment. But remember, we're not quite finished, because these carbons here have only got 3 bonds. They're not happy. So if you think about it, I can keep on building this chain forever, but the ones on the ends are not happy. So I'm going to add 1 more hydrogen on each side to kind of plug the ends, if that makes sense. So that means it's going to be +2. So if I have a look, here we are, Cn, H2n +2. Now that might not make a little bit of sense, but for some of you that might click and it might help. Okay, alkanes burn in oxygen. Balance the equation for methane burning. Fun. Okay, balancing equations. Right, what I'm going to do, okay, is for balancing combustion, it's just a case of going for it really. Don't bother with any of the balancing tables. Let's think about this. I'm just going to put a 1 there just to start off with. Okay, I don't actually need to write a 1 there, but I am going to just for my own benefit. If I have a look in methane, I've got 1 carbon, right? So the only thing which carbon can turn into is carbon dioxide. So for every 1 of these, I'm going to have 1 of them. Okay. Now the only thing the hydrogen can turn into is water. Now I've got 4 hydrogens, and each water takes up 2. So that means I'm going to have 2 waters. Okay. Let's now go backwards and tot up the oxygens. So I've got 1 CO2 with 2 oxygens, so that means I've got 2 oxygens so far, and I've got 2 waters each with 1 oxygen, so that's another 2 oxygens. So that means I've got 4 oxygen atoms in total. And they go around in pairs. So if I've got 4 oxygen atoms in total, they go around in pairs. That means I'm going to have 2 oxygen molecules. Okay, ethene is an alkene. Which reagent is used to test for alkenes? There's no other way of getting around it. We just need to remember it's bromine water. Now, if we need to think about the actual what we see, is bromine water is orange. Okay, and when it reacts with an alkene, it turns colourless. Okay, the test is often called decolorizing bromine water because bromine water is a nice orange and it goes colourless when it goes. All you have to do is put it in, shake it, and it turns. Why are life cycle assessments done? So, life cycle assessments are all about, it's kind of in the name, right? You're looking at the life cycle and you're assessing it of a product. You basically want to see how bad it is for the environment, what energy or resources you're putting into it. And that goes all the way from manufacturer, okay, if you think about a life cycle, that's like conception, birth, raising, right, all the way up to disposal, going through its useful life. Okay, so why are they done? They are done to assess the impact on energy and resources of a product from manufacture through to disposal. Okay, compare the 2 methods for disposal of biodegradable plastic bags. Use the information from table 6. So, lovely. We've been given a table with values. That's going to be key here. So, mass of carbon dioxide produced in kilograms. Well, if I had to top them up, burning and using energy to generate electricity, well, that's used 25. Landfill uses 15, so that's a win for landfill. Uses solid residue in massive solid residue in kilograms. Well, this is 0.05 and this is 0.07, so it's a win for the burning it. Massive sulfur dioxide produced, okay, in kilograms. Well, that's a win for the burning it, because sulfur dioxide is not good. So I don't want, we talked about that earlier on about acid rain. So I want as low amount of this as possible. So 0.2 is lower than 0.3. Okay, so first of all, okay, you can say landfill is better in mass of carbon dioxide produced. Okay, which is 15 kilograms compared to 25 kilograms. But for everything pretty much else, burning and using energy to generate electricity is better. Okay, so burning the waste produces less residue, okay, which is 0.05 kilograms compared to 0.07 kilograms. Produces less sulfur dioxide, okay, 0.02 kilograms compared to 0.30. And crucially, something else we've forgotten. This is generating electricity. Okay, so and it generates electricity, which is generally quite good, right? Because you're taking a waste product and you're doing something with it. So it's kind of a trade-off. Okay, you're going to make more carbon dioxide, but you're going to have less residue, less sulfur dioxide, and it generates electricity. Okay, now because it's compare, you don't actually need to give a judgment. You might want to give a judgment just because you say, because I'm not going to lie, I'll probably say that burning waste is better. Okay, last question. At this point, you're probably suffering. Okay, you're flagging. So last week for exams, banging your head against the table, but we're nearly there. Okay, you see that end of questions. Just before we get through it, always look for the end of questions, because especially because paper 1, for instance, had a question on the back, which is really mean, right? Always look for end of questions. Don't stop until you get there. Okay, every sport says, you know, play to the whistle. You are playing to the end of questions. This question is about the Earth's atmosphere. Carbon dioxide is a greenhouse gas. What is another greenhouse gas? Well, argon is not. That's a noble gas, does nothing. Nitrogen is in the air normally. Oxygen is in the air normally. Okay. I mean, so is argon and methane, really. But the one here we need to know is methane. Greenhouse gases causes global climate change. Give 2 effects of global climate change. There's a plethora, all fancy word, of different things that climate change does. Okay. So I would say, okay, you're melting ice caps, okay, which raises sea level and which causes flooding. Okay, that's actually 3 in 1 really. You have more extreme weather, things like storms, things like hurricanes. You also are going to have what we call desertification. This is where we get an enlargement of the deserts. We also get habitat destruction. Okay, there are many different reasons which you can put down. 4.1 kilograms of a plastic used to make plastic bottles has a carbon footprint of 6 kilograms of carbon dioxide. Calculate the carbon footprint of 1 plastic bottle of mass 23.5 grams. So this is really testing our conversion. Okay, so I've got 4.1 kilograms of a plastic makes 6 kilograms of carbon dioxide. So the key thing is I want to know how many bottles are in 4.1 kilograms. So the first thing I'm going to do is I'm going to convert kilograms into grams. Now hopefully we know that there are 1,000 grams in a kilogram. So if I have 4.1 kilograms, if I times it by 1,000, I'm going to get 4,100 grams. Now each plastic bottle is mass 23.5. So I'm going to do 4,100 divided by 23.5. Okay. Now let's use my computer calculator so I don't get it wrong. Okay, it is 468. Now again, I'm going to round it eventually, but I don't really want to disturb it yet. Now that is how many bottles produce 6 kilograms of carbon dioxide. Okay, so if I do 6 divided by that number, okay, that is going to be the answer. Okay, so if I do 6 divided by that number, I get 0.034 kilograms of carbon dioxide. Now I'm going to do it to 3 significant figures because actually no, I'm going to do it to 2 significant figures because 4.1 is 2 significant figures, so 0.034 kilograms is the answer. Now that's a little bit tricky, okay, and obviously I had calculator delay there, but the key thing here is I know that 4.1 kilograms makes 6. I know the mass of 1 plastic bottle, so I've got to divide 4.1 by 23.5, but remember the fact that you need to do the unit conversion and then I can work it out. 7.4, give one way that carbon dioxide emissions can be reduced when a plastic bottle is manufactured. Okay, so this is quite tricky. Okay, if you don't know it or think it. Okay, first of all is knowing that to make a plastic bottle, that's an energy intensive process to make any object. So you can run or the factory on renewable energy. So if instead of having a fossil fuel power station generate your factory, you could use renewable energy, and then you're going to have less carbon dioxide emitted from generating the energy to make the plastic bottle. Last one, explain how the percentages of nitrogen, oxygen and carbon dioxide in the Earth's atmosphere today have changed from the Earth's early atmosphere. Okay, lovely question. So first of all we need to explain. So we're going to state first and then we're going to explain. So I'm not actually going to write these in full sentences. Okay, let's pretend that I'm got towards the end of the exam. Okay, and I've panicked. Okay, I'm trying to get something down. So if I look at the past and I look at today, first of all there was very little nitrogen, there was pretty much no oxygen, and there was lots of carbon dioxide. If I look at today, I've got 80% nitrogen, so that's overwhelming. I've got 20% oxygen, which is again quite a lot, and I've got 0.04% or very little carbon dioxide. So what's changed? So the nitrogen, well, we actually answered that earlier on in the question, in the paper. Volcanoes, okay, that's what's changed. That's what's explained that change. Now these two are both explained in the same way. What process has essentially turned carbon dioxide into oxygen, right? That is what happened. So I had lots of that and I've got lots of that. And the key process here is photosynthesis. And what does photosynthesis? That is plants and algae. So if I was to put this into photosynthesis, okay, in the past there was very little nitrogen and now there's 80%. This is released by volcanoes, and also you can say the breakdown of ammonia. Oxygen, there used to be no oxygen and there's 20%, and there used to be lots of carbon dioxide and now there's very little, and that's because plants and algae have done photosynthesis, which has turned the carbon dioxide into oxygen. Now that's not actually all of it, there's some other reasons. Okay, first of all, it's dissolved in the oceans. Okay, and that takes some of it away. and that also makes carbonate rocks. So like limestone, that's another kind of carbon sink, something which is taken away. So photosynthesis can explain the oxygen, but it can't explain fully the carbon dioxide. And to add into that, we need to just say dissolved in oceans and also makes carbonate rocks. You can also say, because those carbonate rocks also come from shells, that it makes fossil fuels and they're locked away. Okay, so nitrogen has changed because of volcanoes, oxygen has changed because of photosynthesis, and carbon dioxide has changed because of photosynthesis, but also fossil fuels having been dissolved in oceans made carbonate rocks from shells, and those dead creatures also make the fossil fuels. Okay, that is the 2018 Chemistry Paper 2 Foundation tier. I'll make sure I do the higher questions as soon as possible, i.e. tomorrow, otherwise I'll be too late. I'll try and get that up before the live stream. Okay, hope that you enjoy this format. I know this will go up at a weird time, but hopefully it gives you something to look at anyway. If there's any feedback, any things that you would rather have, okay, it's also, I'm still doing it in a bit of a cowboy fashion with my microphone, my phone, running a webcam app to my laptop, but the one change is I've got a light box now, so hopefully you found the light quality. Let's just show you, it can really whack up, right, go nuts with the white balancing and the brightness, but hopefully you found this video useful, and any feedback is appreciated. I'm not going to go through that whole smash the like button. People who do that can just go away. Cool, thank you.